see each other. You'll have to stay in your quarantine space while we talk.
Welcome to episode 62 of Quarantine, March 19th, 2021. We are now well into the first anniversary of a lockdown that inspired this show, Quarantine, because we all felt a year ago it was rather isolating and we were cut off from ideas, and yet we knew that at the beginning of this pandemic even there was an acceleration of collaboration in our very first show talked about the collaboration in synthetic biology to understand the world that we had arrived at, collaboration that we had seen in countries working together in bottom-up mechanisms to solve the PPP problem. Next week will be our formal first anniversary, and today we want to kind of pull the lens back. We've spent a year in this very immediate present time of accelerated change. Today, we want to pull the lens back and talk a little about the almost the epics of change that we've seen from the Industrial Revolution till now, and how we're reconceptualizing our very notion of machines and the relationship between biology and the mechanistic world. The whole world of synthetic biology, artificial intelligence, that whole world has moved forward with as much acceleration as we've seen in our day-to-day world in this era of the pandemic. And so today we have a very exciting show where we've brought together the world experts on this fundamental question of what is a machine? You know, if you think about it, we draw our metaphors of what a machine is from the Industrial Revolution, from that clockwork universe world that kind of came out of the Enlightenment. Machines were predictable. They were clearly created by humans and not by evolution or Mother Nature. They were inanimate. But today we want to consider the prospect that perhaps we're on the threshold of a new science, machine behavior, which merges this whole notion of organic and inorganic and sees at multiple levels one class able to inherit the traits of the other. So these incredible advances in things like biology and neural networks and cognitive and computational science show us that increasingly machines have traits that may be as complex and at times as difficult to understand as life itself. So, Mickey, we have some amazing people on the show this week.
We do. Hey, Peter.
Help us consider this.
Well, and I think I think it's worth noting that you said machines are inanimate. Actually, no, machines do things. That's good, but and you can't say they're not sensate. They actually have sensing and they have the ability to do things. But this understanding that sometimes we can't explain what happens inside of like a neural network, an AI machine or that new speaker that I have over there that seems to have an opinion and a mind of its own, or it might make decisions that I can't understand. This notion that there's something going on, there's an inner life of these machines as they're starting to get computation embedded in them is not new in some ways. And I think that's what's exciting about this, is that this boundary line between the metaphors we've used from the Industrial Revolution and what we're now starting to see happen with computation being pushed out to the edges and little bits of sensing and feedback and memory and things coming. There's this emergence of an understanding that we can both learn from and use machines like artificial intelligence or in this case, machine learning to actually help us do science. And in that journey, we're actually finding that we can understand more by doing that about how life arose and how cognition and action and persuadability, kind of emerged even outside of our brain. And I think there's this weird, there was a frisson of excitement when I read some of our authors, some of our guests here wrote a new paper. And my head just felt like it was exploding reading it, because it was not just about we need new metaphors for machines, and it was not just about, where does computation and cognition and all the rest happen, but it was kind of like we had to actually think about both of them in new ways. And it felt like the birth of a new, it feels like the birth of a new science or a new discipline. And that got me very excited.
Yes, Mickey called up last week and said, you have to read this paper. It will reframe how you think. And then I read it, and so we'll meet Michael Levin and Josh Bongard in a moment. But they basically have argued that machines are not what we thought they were, that they have much more of the characteristics of life. And also, we've often had this metaphor, we use the latest version of science to describe complex things or life. So, for example, the brain was a switchboard back when we invented the telephone. And then it was a computer.
Memory is reel to reel. I can see it right behind your
exactly.
head. So I'm pretty sure that's how memory works.
But like maybe we have it better. Perhaps machines are now best understood as living things. So there's a whole set of reframings here that then I think is a really interesting starting point for us to then think about this future where we have new forms of creating material, where we use energy differently. Let's bring on our guests. And basically, we're going to have Michael and Josh, who wrote this really interesting paper. And then we're going to have a couple of ethicists on to understand that. So,
and let's bring on Jana and Jantine as well. So we'll just do a quick intro of all the guests. Hey, everybody. Maybe, Josh, can you give us a sentence or two about yourself? Who the heck are you?
Sure. Yeah. Thanks very much, Peter. And thanks, Mickey. Looking forward to this. I'm Josh Bongard. I'm a professor of computer science here at the University of Vermont, up in the upper right corner of the United States. My area of research is evolutionary robotics, and increasingly with Mike working on what we call biobots. I'm happy to talk more about that in a little bit.
Evolutionary robotics. All right. Michael, how about you?
Yeah, thanks everyone. Great to be here. So my name is Mike Levin. I'm a professor of biology at Tufts University in Massachusetts. And my group studies a sort of combination of developmental biology, computer science, and cognitive science. And we spend most of our time thinking about various bodies and the types of minds that can inhabit them.
So embodied cognition and things like that.
Yep.
And Jana, how about you? Go off mute.
Sorry, I always mute myself. I am a research scientist at the NYU Center for Data Science. I work with a group that builds QA benchmark data sets for large language models. I also work with IBM on their data science and AI blog, and I'm a graduate student at the Maryland Institute College of Art and UX Design. My primary interests right now are actually in language and translation and how to translate concepts and teach them to other people.
Well, I love that you're joining us, and I saw you talk a little bit at an interaction design conference, and I was fascinated by just sort of how do we understand how we interact with these things. And I think one way that we interact right away is that when I want to understand something or explain it to a 6-year-old, I use a metaphor, an analogy, I use a drawing, I use some story. And so language is just one of the ways that we grab a hold of things and grab a hold of ideas. So I'm super excited that you're here. Jantine, how about you?
Hi, I'm Jantine Lunshoff. It's great to be here with you and with my colleagues and friends. I'm a philosopher by training, and I work as a philosopher and ethicist in the Lein Institute for Biologically Inspired Engineering. And I think the term biologically inspired engineering, which is not bioengineering, already gives an indication of how incredibly interesting this is for philosophers. Because what my program is, so to speak, is bio-inspired humanities, because I strongly believe, after having worked very long and closely with the scientists in the field, that what we learn from in the biological sciences, it's going to change or must call into question a lot of the concepts that we use in philosophy and that we have been using for thousands of years. And I think the work of Josh and Mike is a great example of it, because there you have things that never were there before. So that is really an invitation it's food for thought, an invitation to philosophers, and of course also for ethicists in the extension of that.
I don't know how many times we've had a philosopher on our show, Peter. I'm not sure. I know that we often get artists because they sometimes are the line pushing into the future by bending and breaking and doing things. But I don't know how many times we've had a philosopher.
This summer, when we were going through a lot of the George Floyd stuff and we were trying to understand kind of the American character, we had a bunch of people who took us back to the Enlightenment and this notion of the individual and this notion of community. And we had Bill Cathers from the Aspen Institute, right? And it was a moment in which we actually had to go back to founding ideas to figure out where we were at and how we would frame things. And I think we're at a moment like that today with science and with biological thinking influencing computation, and then computation helping us understand that, which is going to bring us up to the work that Mike and Josh have done.
So let's we'll invite Jantine and Jana back in a little bit. We'll have Josh and Michael. Actually, Peter, did you want to do any kind of setup on this before we jump in?
So, yeah, I'm basically going to set it up and throw it over to Mike and Josh. But basically, you have this paper called "Living Things Are Not 20th Century Machines," updating this metaphor of mechanisms in light of modern machine behavior and science, and you're basically postulating that the way we've thought of machine, that rather than this like machines are down here and life is up here, you're suggesting we upgrade machines as we make them more sophisticated and imbue machines with more and more biological and genetic and evolutionary characteristics, and that then forces us to realize that these two genuses come together, and then that's kind of a reconceptualization of what we mean about machines and this man-made species of ours that we're creating, right? And that changes both the possibility frontier and I think philosophically how we conceive of these things. So that was kind of mind-blowing. I think we should throw it over to Mike and Josh, first of all, to set up your thesis, and then maybe how you got there.
Yeah, how did you get together to work on this, and then what are some of the key concepts that would be great for us to share with everybody about the paper?
Sure, I can start us off, and then I'll hand over the baton to Mike. Mike approached me maybe 5 or 6 years ago and invited me to a very interesting workshop down in Massachusetts, based around some of the ideas that we're going to talk about today. And some of my work before that workshop was on what I mentioned, this idea of evolutionary robotics. And I'll just briefly set this up for your listeners. We create a computer program that creates a virtual world. It constructs a simulated creature, a virtual robot in that virtual world. And then the supercomputer watches that virtual robot perform in that virtual world and measures how well it does at whatever we ask it to do. If it does a poor job, the computer deletes it. If the robot does an okay job, it makes a randomly modified copy of that robot, tries another robot, tries another one. It's known as an evolutionary algorithm. When you wrap an evolutionary algorithm around robotics, you have the field of evolutionary robotics. So at Mike's workshop, I talked a little bit about this idea. We showed a robot that evolves itself. It evolves the ability to recover after it's been injured in unanticipated ways. And that was sort of how Mike and I got to know about each other's work.
Interesting. And so we're going to come back to evolutionary robotics. Mike, what about you? Now, I remember reading a Nova article about a study that you were doing with flatworms. And my mom, when I was growing up, was a scientist, a biologist, and her thesis was on flatworms and on when you cut them, what happens, and I just was fascinated by this. I mean, she had her booklet in the bookcase, and you'd read it and you'd look at these weird cross-eyed little worms and you'd be like, what the heck? And that was probably one of the first moments as a child that I got so fascinated by that you could do science, that you could do things. Tell us a little bit about, why did you invite Josh, and then how did this paper come together, and where are you coming at from this?
Yeah, so originally, I've known about Josh's work for a really long time, and I thought it was really unique and interesting, because one of the things that we would like to do is understand how cognition in all of its guises, so very, very modest basal cognition, and then all the way up through sort of, human cognition and beyond, how this can be created, how it can be modified, how it relates to the various bodies that these different kinds of minds live in. And we're interested in things like memory and decision making. And these worms that you mentioned are an excellent example of this, because if you take a flatworm and you cut it into pieces, every piece needs to make, the cellular collective needs to make decisions about what it's going to grow, because reliably these things are able to recreate exactly what's missing. So head, tail, whatever else is missing, it makes the exact correct thing at the right location, and it stops when it's done. The fact that it stops when it's done means that the system as a whole has a set point, a stop condition for this error minimization process, right? So here you see this whole microcosm of decision making, of being able to store these large scale pattern memories.
But even grow a head implies grow a brain.
Yeah.
Or grow, okay, and it's goal directed in many ways, right? It's actually correct. Aiming for a goal and knows when to stop.
That's correct.
Okay.
Yeah. So here, this is sort of we treat these kind of morphogenetic models, the embryos, tumors, regenerating limbs. All of these things are models of collective decision making, and they're models of scale up of cognition from the very modest goals of single cells, somehow scaled up to these very large anatomical goals. And so I was very interested to work with Josh on getting a computational understanding of this kind of process.
And so I'd love to maybe, Peter, do you want to show the Nova clip? Because I think that actually gives us something very visual to think about, and maybe the flatworm, we can have Mike explain this a little bit, and then we can dig in on the paper more, and sort of what came out of the act of writing the paper, like what were some of the key moments.
So today, what's amazing is we're going to get into what you're postulating is this new field, machine behavior, which you got to because you started looking at the smallest units of biology, which were doing things like decision making and evidently thought down to the singular cell level, and then that model helped us start to think about machines. So to begin this journey, here's a clip from Nova, and it talks about slime mold. And the fact that slime mold, if you let it out, figures out where the food is. And if you give it a choice between food it's supposed to get good nutrition from and not, it will figure that out. And then if you were to take it away and merge it with other slime mold, it would actually have that knowledge. So there is memory and learning going on in slime mold. So let's take a look at this clip in which we see an experiment, and then we see some of Mike's commentary.
Slime mold capable of remembering? Is it capable of learning? That question is the Holy Grail.
Proving that Physarum had these capabilities could show that a single-celled creature was capable of intelligence and might very well force scientists to reconsider the idea of intelligence itself.
So we set up an experiment to see if Blob learns things. A habituation experiment.
The objective was to try and habituate Physarum to a substance it was repulsed by. In this case, salt. Between this Physarum and a tasty snack is a bridge a few centimeters long. Normally, Physarum makes the crossing in about an hour. For her experiment, Audrey coated the bridge in salt. Not enough to harm Physarum, but enough to leave a bad taste.
It took Blob 10 hours to cross the bridge. The next day, we do it again.
By day 2, that same Physarum was moving faster over the salt bridge.
This time, it takes 8 hours to cross the bridge.
Audrey repeated this for 5 days, and each day, Physarum moved more quickly across the salt bridge.
By the 5th day, Blob takes no more time than our control blob that crossed the bridge with no salt. So Physarum ends up getting used to a substance it doesn't like.
It seemed that Physarum learned to tolerate or habituate to the salt? Had Physarum actually learned that the salt wasn't harmful? If this were true, it would mean that somewhere inside Physarum, there was a form of memory.
Audrey showed very nicely in her work that Physarum clearly has memory and learn from its experience to adaptively make decisions about where it's going to go and how it's going to explore its environment. All of these are fundamental components to being smart.
Director of the Allen Discovery Center, Michael Levin, listens in on the electrical signals exchanged between cells.
My lab focuses on bioelectricity. All cells are electrically active, and these electrical signals enable cells to join into networks that store memories and process information and make decisions.
So, Michael, that was a fascinating introduction to kind of an ever smaller unit of things that have memory. And then this really was related to other work you were doing on cells and learning.
Yes, correct. So we look at memory and decision making in single cells, and then the scale, and in fact even below. So we're even looking at memory in molecular networks and trainability in molecular pathways and genetic networks and things like this, and how this all scales up into cells, tissues, organs, swarms of organisms. The scaling of cognition across the tree of life.
I think that's interesting too, in that it hints that maybe our notion about the supremacy of the brain, our notion about that kind of stuff, all kind of comes into question, because you start to realize that there are all these weird feedback loops and all these, whether it's chemical gradients or other things that in some way cause this emergence of aspects of cognition. Michael, why is this interesting to you? Why do you care about this, as a biologist?
And Mike, could you explain? One of the viewers in the audience asked what single cell creature that was. So maybe you could also tell us what the blob was.
The blob that you were looking at is a slime mold called Physarum polycephalum, and we use it. It's a particularly interesting example because the whole thing is one cell, and it can be extremely large. It can be a meter in size or so. Oh, wow. It can be quite large, but the whole thing is one cell. And there are no nerves, there is no there's no brain, no central nervous system, and it's not a terrible surprise in the sense that biology was solving problems long before brains evolved, right? So the ability to confront novel circumstances and to use your past experience is way older than brains, of course. And why is it interesting to me? I mean, it goes to really core problems in philosophy, in the sense that all cognitive agents are made of parts. So there's no such thing as this like unified single cognitive agent that has beliefs and memories and so on that belong to that agent, and that's it. It's this like, sort of indivisible. So that doesn't exist. So we are a collection of neurons and other things. All cognitive agents are parts underneath. So what we really need to understand ourselves and to know what does it mean for you to have memories, beliefs, and preferences that belong to you, but not to all the individual cells that you're made of, right? How does that scaling work? What does it mean for the subject of cognition, of personality, of memory? So that's kind of in terms of the philosophy of mind and asking who we are and how do novel minds come into being in the first place. This is really fundamental. We really have to understand that scaling from pieces to the whole.
It sort of reminds me of Leaves of Grass, of the poet from about 100 and some years ago that said, that we are legion. We are made of many things. I'm drawing a blank on his name now. Why is this?
Walt Whitman.
Walt Whitman, yeah. So, but I think it also seems that in your exploration, you're also really interested in looking at things like cancer, and if it might be a developmental problem, and if there are actually ways to kind of teach the cancer to become not cancer anymore. Can you say more about that? I'm probably completely butchering this.
Sure. No, you're on the right track. And this was an idea that was popular at the dawn of the biology of cancer, and it later sort of fell into disfavor as genetics and molecular biology took off. But the idea is that the real question isn't why is there cancer. The real question is why is there anything but cancer? Because individual cells are extremely competent. They can solve all their needs at the level of, think about an amoeba, right? It gets around, it handles all of its metabolic needs, its behavioral needs, and so on. And in order to have a stable organism, all of those kinds of individuals, so those cells, have to work together towards a grandiose goal. It has to work together towards the maintenance of a liver and kidneys and various other things. These are goals that cannot belong to any one cell. No individual cell knows how many fingers you have or what a finger is or what shape you're supposed to be. It's the collective. And so in order to have anything like a multicellular organism, there has to be a collective intelligence that is created from these cells working together toward very large, long-term goals, goals that are months and years long, which single cells, of course, don't do. And so what happens is when that process, and that's a very complex process, when that process goes awry, then you get what we often call cancer. And of course, cancer is very complex. There are many ways to get cancer. But basically, when individual cells become unplugged from this network of communications that binds them into this larger individual, their boundary of the self shrinks. Instead of the self being this whole organism, it becomes very small, right at the edge of that single cell. And when that happens, this boundary between self and world gets real small, and then the rest of the body is just environment at that point. At that point, it's just an amoeba living in this environment. And what do amoebas do? They go where they want, they reproduce as much as they want, they eat what they want. And so you get this process of metastasis. And this is part of our work, where we've shown that you can generate a metastatic phenotype with no genetic damage whatsoever, just by perturbing the electrical communication between cells. And then better yet, you can actually repair it by going in the opposite direction.
This inability of the cells to work together, I couldn't quite tell if you were describing the United States Congress or a current political condition or the factors that went on in a cell, right? There's such a amazing philosophical connection between all this stuff.
Well, this collective action is maybe at the crux of this too, right? It's just this sort of and a lot of people have said, or biologists like David Sloan Wilson and others have pointed out that evolution didn't stop when we suddenly had multi-celled organisms. Humans are master cooperators. And why is that? What was the evolutionary goal of being a cooperator? Why do we make cities? Why do we build civilization? And it does feel like there might be some underlying patterns and theories that could help there. Josh, I'm curious about your angle on this. So after you went to this workshop and you shared a little bit about the work you were doing, maybe give us a little bit more insight into maybe a really core component of this that you really wanted to make sure got out in this new paper that you've been looking at.
Sure. So as I'm sure all your listeners have already figured out, Mike's work is incredibly exciting. It's been a really interesting collaboration. We were just talking about what's sometimes known as neurochauvinism, equating intelligence, with brains, or Mike gave another example, equating cancer with genes. These are really interesting questions that have deep philosophical roots. But as a roboticist, there are also practical implications of, having the wrong metaphor.
Yeah.
We are all maybe too aware of emerging AI technologies, which are based on neural networks. They're extremely powerful technologies. And we're getting to the point where 99.999% of the time, they do fantastically well. But that remaining 0.001%, they do fantastically stupid things. We don't know how to stop it. We don't know how to predict beforehand that it's going to do it. It seems there is a pressing need, a real economic need to readdress this question of, should we be trying to make smart machines by programming simulated brains into them? And this is part of what I find so inspiring about working with Mike, is trying to approach making machines in a different way that changes the way we think about machines and intelligence and all sorts of things, but also hopefully will ultimately make powerful and safe technologies.
Well, and I think it's weird. I would say when I saw your Xenobot clip, there was a part of me that felt like, oh my gosh, this is hubris. Like that. I'll just tell you. I mean, that's what I first thought, right? but in a sense,
You're
it
not
also,
the first person to say that. Don't worry.
yeah. But I think it's humbling to see how, to just appreciate life, like to see the amazing ways that life has figured out how to solve some of these problems. And so there's this weird kind of like, oh my gosh, we can do crazy things. It goes back to like Stuart Brand saying, we are as gods, we might as well get good at it. And that kind of a notion. But it also forces you to be more humble, I think, in that you start to see like, okay, what is actually happening? What are some of the things you want people to take away from the paper that you both collaborated on?
So you mentioned machine behavior, and this was a central theme in our paper, and we can definitely talk about that. It's not our term. It's a term that comes from a Nature paper from last year. I was one of the co-authors. There were many other co-authors. The primary author was Iyad Rawan, who's now at the Max Planck Institute in Germany. And part of his thesis in that paper was to say, listen, we need to think seriously about the science of machines. We are creating these intelligent machines. Some of them are these powerful machines. Some of them are so powerful and so complex, we don't know how they work. We can't predict them. Let's turn to some other branches of science and psychology and philosophy that also grapple with trying to understand things like humans, where we're not always able to predict how they work and what they will do. So Mike and I were trying to continue that momentum of what exactly this field means.
Well, and I think this behavior notion, machine behavior, and this notion of thinking about new ways of thinking about this, I suspect we've just come through watching what happens when we sort of naively exploit what we think is science or we think is technology with things like the challenges of dark patterns in design, user experience patterns that strip mine your cognition or that help you think black is white or white is black. And it's because I think in some ways the soft sciences were called the soft sciences in like maybe the 50s or 60s by the military. And they're probably the hardest sciences of all. I think it's really hard for us to get our hand around this. And often in Silicon Valley, people just sort of avert their eyes and go, never mind. We're just going to do the cool things. Let's do this. And I think you're forcing us to realize that we probably have to get smarter about behavioral science, about social science, and writ large, and think about some of those aspects.
I agree. And which is hard and which is soft, I don't know, but we've solved a lot of the technical issues. We can make pretty powerful machines, and now we're grappling with how do we regulate, how do we legislate, how do we prove that they will do X and Y and not Z. It is definitely a big challenge.
Mike,
what's one of the...
I was just going to say, Mike, in the paper, you set up contradictions or several things we commonly think about machines and life, and you suggest perhaps they're closer. For example, you talk about, we think machines are independent and life is interdependent, but of course, increasingly machines are in interdependent systems. You talk about, we think machines are supposed to be predictable and life isn't, but is that true of machines? Machines are designed by humans and life is evolved. And life is hierarchical and self-similar, and machines are more modular. Walk us through some of these traditional conceptions of machines and why that's changing.
Yeah, let's first just go back to why this whole notion is interesting, and many really smart people in the past have argued either on one side or the other as to whether the machine metaphor is a useful way to look at living things. Mm-hmm. And I think that whole debate, interesting as it was, needs to change in two ways. And the first way is that oftentimes people use this as a binary category. So it's either a machine or it isn't. And let's define what's a machine and what's not. So I think this is deeply mistaken. And I think what we actually have is a continuum, and we have a continuum of machine-like behavior in various ways. And so what you have then is a continuum of different bodies and the different types of cognition that inhabit them that along this continuum are very, very simple things and slightly more complex things. And I've sort of been calling it the axis of persuadability, in the sense that on one end you have systems that are basically not persuadable. They are mechanical, clocks and things like this, where your only hope of changing their behavior is by readjusting the hardware with a screwdriver.
Yeah, they are determined to keep counting those damn seconds.
There's just nothing,
all the time.
There's nothing else that you can do. And then sort of a little bit further up the axis, you will have things that can be controlled by stimuli, right, by experiences that they have. And then further on, you may have things that can be rewarded or punished, so they can be given positive and negative reinforcement. And eventually you reach systems that are so complex that you can actually interact with them via reasoning. So you can actually give them facts. So you're not physically altering their hardware, but of course you may be forcing them to change their structure by giving them cogent reasons that they, as rational agents, can't help but follow you along with whatever you just you tried to convince them of. So
that's sort of the rise of storytelling as a method of persuadability or something.
Yeah,
the narrative. Yeah.
Exactly, and so you have this smooth continuum of increasingly more sophisticated cognitive agents, and the important thing is, one of the things we tried to say in this paper is that things that used to be easily recognizable as machines some decades ago, things that were metal and clunky and predictable and made by man and all these kinds of things, versus living things. It used to be pretty clear that, hey, those live on one end of the spectrum, and then the living things more or less live on the other end of the spectrum. That isn't true anymore. So those kind of things are found everywhere. We have basic living creatures that are and even subcomponents of those creatures that occur everywhere on the spectrum. And we increasingly have our artifacts, human-made devices that also live everywhere on the spectrum. So we need to ditch that binary classification. We need to realize that a lot of the arguments that have been had in this field use definitions of machines that are simply no good anymore. They used to be reasonable. They just don't live up to, as often happens, engineering and technology has gotten further along than some of the philosophy on this topic. And so things that people often will write about machines or this and that, and life, of course, isn't. When you start to think about these categories, it becomes obvious that there's no reason we couldn't build machines that do these things. And in many cases, we already have. Right?
Yeah.
We need to come to grips with this. And fundamentally, the reason this whole question is even interesting, I think, is that the notion of machine, and what is a modern notion of machine that's actually useful, right? That can demarcate something in the modern world, gets to the question of creation, prediction, and control, because it asks us to think about where do things come from. And Josh's brilliant work shows that kind of amazing things can come from this evolutionary process that oftentimes people treat as blind, blind evolution. Well, guess what?
Blind watchmaker.
Blind evolution can do amazing things, right? And can give rise to cognitive agents. And where do things come from? And can we understand them? And what does it mean to be able to predict and understand a particular complex system, whether it be living or non-living, And then the question of control. So how is it that you interact with the system? And our point is, so this is really important. Our point is not, and I think a lot of people are really afraid of this, and that's why they sort of, people often feel that something's wrong when you stretch this machine analogy, because what they think is going to happen is that we're going to start relating to people and living things as if they were machines. And I think that's exactly the wrong way to look at this. That's not the point at all. We cannot relate to living things as if they were old school machines, because they clearly are not. But what it does mean is that we may need to relate to complex advanced machines in some of the ways in which we would relate to living things. For example, by asking what their preferences are, by asking what do they know, what the metacognition is like, by asking what are their goals, and can we cooperate with these goals, can we communicate with them? It's going to be, we're increasingly making artifacts that are further along on this axis, where it's a communication, collaboration, and persuasion process. It's not a rewiring process anymore necessarily, right? So
do you think there's going to be the rise? I mean, you just made me think of this, and we talked about reasoning and being able to convince agents to do things. It makes me imagine that at some point we will have religions, lots of religions, like the Protestant Reformation, pop out of machines, because they will have a lot of correlations, maybe not causality, and they'll, that's actually part of. I know this sounds like a crazy question, but I just feel like, will we end up with lots of machines that have religion?
Mickey, I think actually it's a great question. And again, if you tend to think about traditional machines as these clockwork, dumb, there's no one home, how could they possibly have something like religion? I'll give you one example from my own work. We evolved a physical robot at one point where that robot's job was to build an understanding of itself. Do I have a leg over here? Do I have a wheel over here? Is there a small hill in front of me?
Kind of proprioception or something, or
yeah, use proprioception. It was actually a very simple machine, like a virus or a bacterium. It looked like one of my students nicknamed it the Evil Starfish, but it's that's wherever it is on this level of actual sensor motor ability, it was pretty low. We expected or hoped that it would build a perfect model of itself and use that model to make predictions. If I go to the edge of the table, I'm going to be in trouble.
Because I know my inertia or my something, yeah.
To me, one of the most interesting things in retrospect of that experiment was the robot consistently formulated a wrong understanding of self, which was very surprising. Why would it do something? And it turned out that the wrong description was good enough for what it needed to do. And the perfect description of self was too complicated. It required too much thinking. It slowed things down. So it would consistently tell itself a fiction. It didn't know that it was, as Mike mentioned, it didn't have metacognition. It knew about itself, but it didn't know that itself.
This also sounds like every cognitive bias I hear about every day is this sort of, we have these shortcuts. They're not necessarily bad, good or bad. It's just a bias, like a piece of corduroy pants.
Sure,
I feel like it's time to bring in Jana and Jantine, because I feel like now we're getting into some really interesting philosophical stuff. Both of you have had a chance to listen to the beginning of this conversation that probably could go for a really long time, but it's just the beginning of something. And I'm curious what your sort of thoughts are, responses. Just a note, Jana, you're on mute, and kind of your reactions to what Michael and Josh are talking about.
I'm just going, I have a lot of thoughts, but I'll start with the concept of intelligence as computational, as machine-like, actually has medieval antecedents with the work of Raymond Lull in his Ars Magna. And I mean, even the concept of human as machine dates back to, you could date it back to Leviathan, but it also, there's a book written in, the 1730s, I think, called Mana Machine by Julien de la Mettrie. These aren't new concepts, or even the concept of emergent intelligence. If you look at Conway's Game of Life, if you look at Stephen Wolfram's A New Kind of Science from about 20 years ago, and it's discussed in great detail and Catherine Hales in her work, especially My Mother Was a Computer. There's like definitely lots of discussions that have gone on in this vein for a long time, not specifically maybe with this in quite the same way you are, but there's lots of parallels that have already existed in these conversations about how we relate to machines, how humans and machines interact. I personally know two researchers who do work in this field, Holly Peck, who I believe is now at a company called Soul Machines, and actually someone who's a good friend of mine, my friend Julie Carpenter, who actually has done research with human and robot interaction in military service and actually in sex robots as well. This sort of work, there's a lot of work that has gone on in this field. And a lot of these questions, I can't even go into all the detail of all the knowledge I have. I wrote an entire page of notes listening.
Awesome. Well, and I think that's, this notion that of course we've thought about these things. I'm just fascinated by this notion that these things, I think in the paper, you both say all metaphors are false, but some metaphors are useful. And I think, and I really like that notion. And I'm kind of curious, Jana, maybe from your notes, what did you resonate with, or what do you want to disagree with, or what might be an area that would be fun to push around on?
There's actually something specifically I drew from the paper that I actually found a little troubling. And to quote, and I quote directly here, until very recently, the very fact machines could be rapidly disassembled into their component parts, repaired or improved, and then reassembled was one of their primary advantages over living machines such as domesticated animals or human slaves. And I mean, while you could argue that, yes, human slaves were seen as machines, I mean, that's a statement that needs a lot of ethical unpacking. And it also can translate into intelligence in machines. I mean, if we create things that are identifiably intelligent, are they going to be intelligent like animals, which we slaughter and eat anyway? Or are they going to approach some kind of human-like intelligence, human level of intelligence? I do not think it will be the same, because software, emergent behaviors and single-celled automata or other sorts of things, these Xenobots, ideas like this, they're going to have a different kind of intelligence. How are we going to recognize that intelligence and not treat them in a way that's, treat them as our equals? Would we there's a lot of things to think about. We only kind of recognize human life as intelligent, like quote unquote intelligent, despite the fact there are clear signs that many animal species aren't quite intelligent as well.
Well, I was recently reading about the fish, I think there are fish and there are crabs that clean other fish, and like sharks wait in line to actually be cleaned by these fish, and the fish take a little nip out of them. And it turns out that they pass the mirror test of self-awareness of themselves, and these crabs do as well. And that was from Peter Godfrey Smith's book, Metazoa. And he's been exploring, as a philosopher, the sort of place of where does intelligence arise. What, Mike or Josh or Jantine, what's your sort of reaction to that? Like what are we going to learn? How might we treat things differently as machines? Hopefully we'll learn how to treat humans better too, or animals. But what's the sort of reaction to Jana's comment?
Maybe I'll just make a brief comment. I think your point about the disassembly is an important one. I included that phrasing in there as sort of a nod to reductionism. This idea, Jana, as you said, it's been around for hundreds of years, that divide and conquer. It's a very aggressive, almost violent, ethic that a machine is something to be controlled. I know how all the parts work, and personally, I still see that in a lot of robotics and AI. There's this pride in being able to pull something apart mathematically and delve down into the nitty-gritty details and point at it and say, I know that, I understand that, I can put it back together. But we're moving into an era where that becomes difficult or impossible. How do we grapple with machines or technologies that are opaque, that we cannot, take apart to their atomic components? I think for a lot of people that feels a little bit unsettling or confrontational.
Well, that transition, right? When we first, when any of us first encounter this notion that we're building opaque black boxes that work, but we don't know how, so we probe them, but we're not certain, it's not quite a singularity, but it's clearly a state change in how we look at machines. And in a way, what you've written there shows that at first we're uncomfortable with it, but in fact, there's kind of a whole lot of wonder to unpack and then work with in that space.
Yeah, I mean, my sort of main point on all of this is precisely sort of what Josh said, that in the past you had this rough heuristic by which you said things that are soft and squishy and maybe furry, those we treat in one way, and things that are shiny and metallic and they came off an assembly line, we treat them a different way. And so I think our point is that those categories are not going to be any good in very short order. I mean, we are going to be living in a world where we are surrounded by novel creations, and I don't just mean software AIs. I mean all sorts of combinations of humans with the embodied smart prosthetics and devices with various kinds of brain cells in them, and there's just going to be this incredible option space of novel novel agents at all kind of scales on this hierarchy, and they're going to have novel minds. And it's not just a matter of are they as intelligent as us, because it's, treating something well is not just a function of how smart it is, of course. And so we are going to be surrounded by very novel types of agents. And this is a call to really develop a new set of ethics that are not based on really just very contingent facts about what something looks like or where it came from or how it got here, but actually much deeper inquiry into what kind of a mind it has and what do we owe it ethically as a way to relate to it. And so that's the whole point here, is that you can't use these rough categories that used to be pretty good in general life, but they're not going to be good in our lifetime already.
Jantine, you work. Oh, go ahead. Sorry, Jenna.
Sorry, this is just a quick rebuttal. Jantine should go next. It's just that, you mentioned the word agent, which is of course related to agency. Our laws are based on agency. We sentence people to jail terms because we assume they have agency for their actions. Now, the explainability of models is important for determining agency for impacts. Sophia Moja-Noble wrote about this in Algorithms of Oppression, that the distinct problem with black box algorithms, with privately held companies controlling so much of our public infrastructure, which is what the internet is, it's what Google is, it's basically public infrastructure, means that these aren't accountable for the harms it can cause from, the things she describes in the book about self-image of Black girls when they look up those return search terms from Google, but also to things, facial recognition causing wrongful arrest, to denial of home loans, to, facial recognition leading to possibly being killed. I mean, there's a lot of very serious harms that can come from these black boxes. There's wonder, but they also have real life consequences that really point to this important central point in science, is that you must be accountable to the people who this is going to impact, or it's not very good science. It's certainly not ethical science.
I love it, and we've had Sophia on twice to kind of help us unpack with Kathy O'Neill and others sort of these algorithms that make unlucky people unluckier and make lucky people luckier, and how devastating it is. I do think that's, Jantine, I'm curious about where you come in, and also just the kind of work you've been doing. And I know you collaborated a bit with Josh on this stuff, and I'm not sure if you also worked with Mike as well. Where do you come in? Like, what's your point of view?
So I actually started working with Mike, because Mike is also faculty at the Wyss Institute. So I actually saw Mike on the screens that we have on the wall in the institute. So then I immediately, because I have sort of my, I'm trying to pick up. I have antennas, of course, my professional antennas for things that people are doing or saying that have like philosophical impact, at least what I identify as such. And that was for me very, very clear in what Mike said and presented. And as I read his articles about things like metamorphosis and regeneration, and of course the flatworms and so on, that for me that really was sort of the trigger where I thought like, oh, this is someone who I should collaborate with, because I want to know more. I realized I understand too little of what he was saying, and then you need to know more. And what Josh is doing is even more difficult for me to understand, because I'm absolutely not a computer person. But I must say, in the Xenobots, that came really nicely together. And what is fascinating for me is, as a philosopher, you of course you want to go back to what like terms mean, what concepts are, and what I see, and that is sort of the really the revelation, or indicates to me that this should be a start of new search in philosophy. Even that, of course, many philosophers of biology have been looking into these questions. So it's in that sense not. It's not, I'm not the first to notice it, for sure not. But given the fact that I'm an ethicist, philosopher ethicist, who works on the work floor in what I call collaborative ethics among the scientists, I'm even more curious probably than others, and I get the input from another direction. And things like when you talk about agent, that Jane just said, an agency. And as I first heard them talk about it, I thought like agency, like of a unicellular organism or so. Like, isn't that an inappropriate use of agency? And then I started to examine that, and after some time, I got into this world in this parallel world of these of the other way of looking at concepts. And so, for my part, I also as an ethicist, I would say that it's like sort of one warning or one area which is for me more remote. That is, well, how to move, where is actually this jumping over to the realm of normativity of ethics. And what Josh just said about, or when you were discussing religion, that is for me very far away, because then, like I sort of take my philosophical dissection toolbox and then I think like, oh, if I really look at this critically, what is he saying and what is he implying? On the other hand, it's important what was also mentioned, this role of moral intuition. And you mentioned it like with the word hubris. So you hear about these constructs and then, you think like, yeah, but should that be allowed? Isn't that going too far? Aren't they crossing a line? Those sort of questions, and that is very fascinating. It's actually also in other fields of synthetic biology and in the more conventional.
Did the internet just take a vacation?
I'm here.
I think it did for Jantine.
I think Jantine, it did take it.
Jantine. Actually, while we're waiting, Josh, I'd love you to walk us through, if we could show, because we've talked about the Xenobot once or twice, and Jantine just mentioned it. Maybe Omid, if you could pull up the clip, and Josh, if you could talk us through what we're seeing. I think that would be useful too.
Sure, I'll talk through the first half and then I'll hand the baton over to Mike. So what you're going to see in the top half of this video is the best guess that our supercomputer came up with about how to build a Xenobot. In the mind of the supercomputer, in the virtual world you see in the top left, the supercomputer said if you put frog skin cells, which are the light blue boxes you see on top, if you put those on top of muscle cells at the bottom, you get something that moves. And as you can see in the video now, when Doug Blackiston and Mike's group built one, it was able to do what the supercomputer predicted.
So is it if I remember reading through that, it sounded like you used an evolutionary algorithm. It came lots of weird things of saying, maybe if I put the skin cell here, or if I put it there, and it would come up with all sorts of things that just didn't work, but then it would slowly start to get up with things that worked. And was it also with heart cells, or something that had some ability to pulse, or was that in a different experiment?
So those are, Mike, correct me if I'm wrong, frog heart muscle cells that will spontaneously expand and contract. So we basically gave the supercomputer those two types of Lego bricks, soft plastic parts, which unbeknownst to the supercomputer, were going to end up being frog skin cells. And then other Lego bricks that would spontaneously increase and decrease in volume. And the puzzle for the supercomputer, for the evolutionary algorithm, is how do you put these odd building blocks together to produce something that walks along the bottom of a petri dish? So, and then there's that second video. Oh, go ahead, Jana. Before we do that, yeah, Jana.
So just as sort of an aside, you said all metaphors are false. The metaphor of the supercomputer with the evolutionary algorithm is a metaphor for the Xenobot. So is it false? Is it a good enough model? I mean, that's a question.
Yeah, that's a good question. Sorry, I'm just trying to understand your question. So the metaphor of the Lego bricks or the supercomputer?
Yeah, well, because essentially you could argue that the simulation is a metaphor for the real Xenobot. So is it false? Or is there a certain amount of falseness that just is present that's good enough?
It is absolutely false. We are speaking in English, which can only do so much for us. And I will threaten to bring out the whiteboard and do some math, which will get us a little bit closer, but again, not perfect. Jana, you probably know more than any of us about language and when it holds up and when it fails. Absolutely, all of this description of the Xenobots in natural language is close to what's going on, but not quite.
Well, and I suspect you created some environment in the supercomputer environment, probably being another metaphor, but that had some physics to it. There was some gravity, there was some other thing, there was some friction that you then said that these cells have to work against.
So we gave the supercomputer a lot of hints. We told it quite a bit about physics. We told it some biology. So we told it something about how frog skin cells behave and a bit about how frog heart muscle cells behave. But there were a lot of details that we had no idea about. They're still unknown. So we told the supercomputer to roll the dice. Just where you're not sure, just put some random noise in there. And that made the problem extremely difficult. How do you build a stable building when the parts that you're building that building out of will randomly do things that are unanticipated?
That you don't know. Interesting. And Jean-Tine, I'm sorry, you froze up, and so we lost you at the end. But we just had Josh show. We just talked through the first clip from the Xenobots because you had mentioned the Xenobots. Can we see the second clip of the Xenobot? Romita, if you can pull that up, which is actually taking that metaphor in the computer and then saying, okay, but what if we actually made it? What could it do?
I'll let Mike maybe handle this one.
Sure. Well, so I want to say a couple of things about some of the stuff we were talking about. So the first thing about the metaphors being, the point isn't that metaphors are true or false. The point is exactly the opposite, which is that we should not be spending a lot of time worried about whether something is really thinking. You know, often people say, okay, I think and I have beliefs, but when you say that these cellular systems have preferences or they have memories, that's just a metaphor. And my point is, there's no such thing as just a metaphor. What there is some degree of fit that this metaphor is helping you move forward in towards new capability, towards a better understanding of your system. If there's a particular way of thinking about it that helps you move forward to do better science and help people, then that's a valuable metaphor to some degree, right? So it's a matter of degree. So that's all we mean. With respect to these Xenobots, there's a couple of interesting things that should be kept in mind. The first, these particular ones that you see here are made entirely of skin, and one of the most amazing things that this teaches us is the incredible plasticity of life. So these are cells that were liberated from their normal context, which is a frog embryo. And when they're taken out of this context and given a chance to reboot their multicellularity, is that they actually are perfectly happy to cooperate with each other to build something completely different. So these things have behavior, they have structure, they have all kinds of functions that are, and that you can see them moving around and doing various things here. And there are lots of data that are sort of in the pipeline and not yet published that show us this plasticity. These are wild type cells. These are cells with normal frog genome. If you were to genomically sequence them and try to make a prediction of what they would look like, you would say they should look like a tadpole. Obviously, that's not what they look like, because it turns out that there's this remarkable plasticity of normal cells to do new things. They cooperate with each other to build other functional bodies. And one of the things this does for us as biologists, let's keep in mind one of the important uses of this. So useful synthetic living machines, of course, is one use. But what's really critical for regenerative medicine, and so we're talking about healing people with traumatic injuries, with cancer, with birth defects, right? So this is really important stuff. Is what we're missing in that whole field is an understanding of how cellular collectives make decisions about what they're going to build. The answer to that question, if we understood the rules of morphogenesis, if we understood how it is that cells with various types of genomes build one thing rather than another, we could address most biomedical needs, right? So new organs, repair birth defects, normalize cancer, all of these things are downstream of this very basic question of where does form come from? And you don't get that from straight up genetics. There's a lot more missing here. And so the reason these guys are important is because unlike all of the other standard model species that people study, zebrafish and frog and fruit fly and all that stuff, all of those things have a long evolutionary history. And when people ask, why does this thing fly, or why does it have vision that's sensitive to a particular wavelength, or whatever it is, the answer is usually, well, because over millions of years, the ancestors were selected for this and that. That type of story can't easily be told in this case, because these cells were evolutionarily selected to sit quietly on the outside of a frog and keep out the pathogens. They were not selected for the ability to work together and do all the kinds of things that we have seen them do. And so this novelty, this capability of building new things, we have to understand it, and we have to learn how to modulate it so that we can actually do this in vivo for human patients. Okay, and this is very important stuff. I get phone calls every week from people who have spinal cord injuries or birth defects or various kinds of traumatic injuries, and their answer is always the same: hurry up. What's taking you guys so long? We see all this stuff about the human genome and all these stem cell biology and all this stuff. Meanwhile, where are all the promises of regenerative medicine? So these are the kind of, when people talk about the crossing lines, or this is what's actually at stake, right? Is we need to be able to have a principled answer to people why it is that we do or do not have therapies for these kinds of things. And
this brings us to the experiment that Nova covered, where you started looking again at the form of your flatworms and trying to figure out, how do we influence it, what causes that, and tell us the story of how you applied supercomputers to that over many, many generations, and then how that same approach is being used to try to understand melanomas to see if cells can be programmed to not do that.
Yeah, this is basically the idea that when we try to understand why cells work together to make healthy organs as opposed to tumors or metastasis or whatever, oftentimes the models that we make are extremely complex, and you can't simply look at them and sort of realize, oh yes, I see, if I pull on this thing here, then everything will jump right back to. So we use the tools of machine learning, and one of those tools is the kind of thing that Josh's lab does, which is evolutionary computation to look at the space of all possible interventions and ask which of the many things you could do to the system is going to get it back to the correct state. And so some years back, we used a system like that to build a model of the electrical communication between cells and ask it, in the cases where, we've done this now twice, once for cancer and once for brain defects, and ask it the simple question: when you have an incipient defect, let's say fetal alcohol syndrome or a genetic mutation, what would we have to do to the system to get back a normal brain with normal cognition, with correct gene expression, all that stuff? What would you have to do? And these machine learning techniques are very powerful to help us use the insights of biology towards therapeutics, and that's one of the things our lab does.
I thought what was fascinating about the Nova one was just that you used, for one aspect of this, it was planaria or flatworms, because they're the most studied in some ways. There are papers about them, science papers that go back a century, and your team looked at, not looking at a sort of bag of words the way that maybe Google might try to figure out how to translate from one language to another, but really looked at the scientific signals and the language used inside of the science papers over 100 years, and tried to figure out a way to consume those, and then run a high-performance computer to kind of try some evolutionary algorithms on this, to find a way that even after 100 years, we still don't know why when you cut a planaria this way, it grows two heads, or when you cut it this way, it does this other stuff. But over, I think it was something like 6 billion iterations or something. I mean, it was a crazy number, that it finally came up with a signal that said, this is maybe why. And then you took some papers that had not been given to it as training data, and it actually validated those papers and identified some new pathways that maybe nobody had done experiments on. So to me, that was a signal that science might be changing. Like just the way we do science, because we can enlist computers, in a way, we could actually have science tell us sort of some of the undiscovered public knowledge that we have hidden in all the science we've done in the last 100 years, and start to see patterns in even maybe the protocol was bad for one of the scientific experiments, or what might be a better protocol.
Yeah, well, so just to be super clear, I want to be really clear. So what our system did not do was read the papers in English. Right.
No,
So we did not analyze the wording. We did not analyze the text. That's not what we did. So what we actually had to do was go through the papers ourselves and simply build a database of everything there is to know about planaria, in terms of, here's the experiment that was done and here's the outcome. And we built up a database of 1,000 or so different experiments. and then search through the space of possible models to the possible explanations for what could be going on inside a planarian, and find one that, when you did these kind of perturbations, optimally gave the same results as people had found in the literature. And it actually did find a human understandable model that explained a lot of the observations that actually people had been looking for many years and not found. So it was cool, because it was part of the sort of robot scientist field, where what you have is a tool for human to help human scientists crank through the incredible mountain of findings, but not simply number crunching, but actually part of the most creative part of our job, which is to come up with models. Otherwise we sit there and we sort of scratch our heads and we say, what, maybe it's this, maybe this thing goes over here and it does this, right? And then we test those models. And that's what this was able to do, was actually help us discover a new model that we could not have come up with ourselves.
John Teen, I think you had some comments about some ethics side of things. I wanted to see what you wanted to weigh in.
My computer completely closed down without any human understandable cause. So I could revive it, but so I apologize. Yeah, I was going into this. I think it was the point of the moral intuition, and referring to what you mentioned, which is very important in societal discussion, this notion of hubris. This question, like when you for the very first time hear about these things, say not even as a professional philosopher, but as anyone, you immediately have this intuition like, oh, isn't this going too far? Or can you make that claim? Or, is this good or this is terribly bad? The interesting thing with moral intuitions is that also professional philosophers and ethicists have moral intuitions. So when you first hear or see about the thing, you can't stop that. You think like, oh, he did, or this is really. But of course, when you're a professional, the professional part of it is that you take out the toolbox and you start the analysis. And that is both for, say, normative, for ethical aspects. It's also for the conceptual part. And I think in the work of Mike and Josh, these things are also connected, because like I heard him saying, and of course I fished that out immediately as I read for the first time one of their articles, like decision making. Well, how can such a cellular construct or a unicellular living organism in this case, like make a decision? Because the moment we say decision making, we also think about, like ethics, like and the agency, like an agent is responsible, and Jana said it, and there is it gets a whole tail of morally loaded connotations, but like it's all based on our world and our concepts, and it was really an sort of an enlightening tour to go back to jump over this intuition, like, well, how can they say decision making when they talk about a unicellular organism or such a Xenobot? It's deciding where it goes. Yeah, come on. So to analyze that, and because it tells me, what do we mean when we say decision making and agency? Apparently, there are also other forms of agency, and that is exactly the fascinating point of what I call like bio-inspired humanities. When we see and hear and really, go into these new developments, it sort of necessitates a revision of the way we think about using those terms, and the further consequences that even you also are going to look more critical at, say, the conventional way we are using it in. So in that sense, it's really an enrichment of philosophical theories and our conceptual understanding. Because we never had a comparator, and now suddenly we can place it in that perspective. And I think that's really the point, the challenging point where progress is going to come from.
Hey, Jana, I think you have to get going, and we really appreciate you staying. We naturally ran right over the 5 o'clock hour here in the West Coast. Thank you so much for joining us.
I had a great conversation. I just have an impatient child who wants to go to the bakery and get her afternoon treat.
Yeah, and anyone else who needs to bail, we just kind of kept going because it's always fun. We always seem to have an overtime. But thanks for joining us. I think it's just the beginning of a field of inquiry. I do think, Jean-Tine, your comment about we now have something else that forces us to think about this because we can understand, or we can start to see agency and decision making in places we never thought it was there before, or something. That feels interesting to us as well. How does that open up your aperture for philosophy? How does that open up your toolkit for ethical exploration?
Yeah, it is an addition to the toolkit and to the perspective in which we pose our questions, for example, about the decision making, and then you need to say, is it only a different use of language, or is it something that is completely novel? And of course, part of this work brings things that are completely novel and forces even a more profound rethinking. But if you have not started from looking at questioning from what perspective am I looking at it, you cannot move on to the new concepts. And then the whole normativity, like the question about ethics, that we also need to rethink a number of the statements that we would make there, or assumptions that we make when we use the word agent or agency, and things like decision making. And the interesting thing, because as a philosopher, I also like to go back in time and look into the literature. And as I learned that from Mike about the decision making, I did find one original article out 1888.
Oh wow!
Where the first explanation, it's in German, and I got it from a New York library, of what biologists simply call chemotaxis. And of course, you can say that is decision making. But if you speak the language in the other world, in the non-biological world, then you're very irritated reading such terms. And that's exactly the interface where it's interesting for philosophers to work. And
I think what's exciting about this
concept of living. And the moral implications of living.
Yeah, what is alive? What is living?
What is alive?
But I think what I love about you said that you're on the lab floor. You're cooperatively and collaboratively working through ethics. That feels like that's so important, and I suspect we're going to have more of these challenges as we have to be interdisciplinary. As there is, this one field has climbed a mountain. And then they realized that there's another mountain over there, and they were local hill climbing, and they have to play with somebody that actually learned maybe truth is a very different thing, because they went to school and the books they read and the jargon they use is a slightly different language. And I feel like the hard work in some ways is interdisciplinary work. It's the work of saying we should have an ethicist actually wandering the floor. It's the work of saying, how do robotics intersect with biology and things like that. And we don't necessarily teach people how to be good interdisciplinary collaborators, because disciplines have kind of sliced the universe up into cute pockets that allowed us to study and get degrees and things, but they're entirely artificial. It's not like the universe was sliced into disciplines. There's a much broader thing, and now we're even starting to get novelty that crosses these different boundaries. So what's it been like working with biologists, with roboticists, with, I'm kind of curious about what that journey has been for you as a learning journey.
I think that term learning journey is very appropriate. One of the issues with my profession is, of course, so many people have no clue what philosophers do. So some people say it like openly to me, wow, almost like, are you alive? I never saw a living philosopher. Wow, really? And I have this one. I have weekly office hours, also open office hours, and as it was still that I was sitting around, I had it today online. One of the colleagues of the week came to me and said, "Are you really a philosopher?" I said, "Yes, I am." And then so it's a colleague from Greece, and then he said, "And do you know about Plato?" I said, "Yeah, well, that's also part of my, so." And then it ended that we till 7:30 were talking about classical philosophy, and I missed Shuttle and whatever. But so this is really it's also a role of bridging these two worlds, like in person. And it's important to make clear that as an ethicist, people often ask, "Oh, are you from the IRB?" No, I'm not from the IRB. And so I am not studying scientists as persons or their motivations or judge their motivations. No, I am, and that is very, very, the work with Mike and Josh is an excellent example of it. I study their work and not their persons, even that you're nice guys, but I don't study you, don't study you.
So just for people who don't know what an IRB is, can you back up just for a second?
An IRB is the ethics committee of institutions that need to approve science projects.
If you're going to do this science, you've got to do the IRB. But you're not doing that. You're actually looking at what does it imply for philosophy,
so I'm not the ethics
for
police, I sometimes say that.
Yeah.
But as a philosopher, but also as an ethicist, I'm building and contributing to my own discipline by learning from and working with scientists, specifically those scientists who are working really at this interface where you introduce new concepts, something like cognition. Okay, yeah, but cognition is not basal cognition. What do you mean with basal cognition? Well, to understand that requires really some reading and talking with people like Mike and Josh to understand, well, what do they mean with that?
By the way, Mike, what do you mean by basal cognition? Because I know that triggered me earlier in the week, and I had to go back and read the other paper you sent about that. But that's this aneural. It's sort of not in brain. It's more basic or something. Is that right?
Yeah, let's just take a slight step back. So I think we're committed to two things, right? All of us, and tell me if I'm wrong. I think we're committed to a naturalistic worldview where humans are not magic, where whatever properties that we have, let's say we have true decision making and true real beliefs and real preferences and whatever. It's not because we're magic. Okay, so that I think we agree on that, and I think we agree that we have to take evolution seriously. So what that means is that whatever capacities we have for these kinds of, full-blown decision-making, moral, ethical, whatever it is, there are simpler versions of this all the way down the tree of life. There have to be, because these things don't arise out of nowhere unless we believe that we're somehow magic. So I think inevitably, no matter what, you have to take all of the things that we think we as humans have, and then you ask yourself, well, what did that look like in other forms of life, whether they be natural forms that are more simple, whether they be in artificial forms that are created, whatever. But what do these things look like in other guises? Because they certainly don't arise out of nowhere. And so when we say decision making and we scale that down, so basal simply means that on the tree of life, we're talking about organisms that appeared earlier on. And so they may be, in many cases, they may be simpler organisms. They may not have the same kinds of structures that we do. The question is, what did the precursors of all of our amazing mental capacities look like in these other forms? Because they had to be there. And so when we say decision-making, basal decision-making, of course, we're not saying that the Physarum has hopes and dreams and it has, sort of carefully considered the moral implications of crawling this way versus that way. No one is saying that. What we're saying is there's a basal version that at one point evolved into the thing that we currently say decision-making when we go to court. But that, of course, evolved from simpler origins. It had to have. There's no other story in the modern world that makes any sense. So this is all we mean. So basal cognition, basal decision-making are simpler versions of all the amazing things that we do now. And by the way, possibly at some point in the future, we will have creatures that have way more cognitive capacity than we do. They will have maybe higher IQs, maybe the ability to care about more things than we can muster the energy to care about. And to them, the things that we do now will seem like basal cognition. The things that we do when we go to court and we say, I morally consider A and B, I have a gut feeling that at some point there will be creatures, they may be biological, they may be whatever, that are going to say, I don't know what that was. That wasn't real cognition.
That was like Neanderthal thinking.
That was
What was
basal.
that?
These people couldn't even.
Do you remember back in the 21st century? Those people, I don't even know what we thought of them as. They were more like pets. Really.
Completely. And we have to take this seriously. We have to understand that there's a spectrum of all these things. Yeah. But
I think actually this whole point, part of this point is that it is so easy for us to collapse down to a black and white, to a give me something simple, because I can't cope with the complexity. But I also think it's this, okay, but you know what? Maybe we're going to have to start appreciating complexity, even if we need to collapse it down into something we can grab a hold of.
Mike, your article and the Nova piece created a real appreciation for the richness of all forms of creature down to oneself things that can actually evaluate and make decisions in their interest. And this may be an obvious question about kind of gut decisions, but I imagine a lot of that basal decision-making stuff is still around today because there's both lower level forms of life, but does this also imply that there are forms of decision-making, or when we say we have a gut reaction because stuff's going on in places other than our brain, and we may have a brain-centric view of the world?
Yeah, I think, in the end, so the way I see this is purely an engineering problem in the following sense. We can have philosophical arguments about whether something is real memory or real decision making or whatever. But to me, the real where the rubber meets the road, as far as whether these are a misuse of analogies or proper use of these kinds of metaphors, is very simple. Does it help you to do better new experiments and get to new capabilities? So if you have a model of cells in your immune system having hopes and dreams about the long future, I dare say that model is not going to help you do better science. And in short order, you're going to find out that no good experiments will come of this.
It's sort of like a dead end metaphor or a dead end analogy. It just doesn't. It actually doesn't open your mind to the possibility.
That's correct, but it's just easy. But the thing is, what people forget. So there's this kind of teleophobia around where people are really afraid to anthropomorphize too much. Actually, you're not anthropomorphizing anything, because it's quite the opposite. It's our job to explain how humans get this. You don't get anywhere by saying that, hey, this thing is like a human. How does a human do any of these things? That's not the direction we're going in. And so people are kind of worried about going too far in that direction. But the problem is it's just as easy to make mistakes on the opposite side. So you leave a lot on the table for regenerative medicine, for biology, if you automatically treat things as not having a particular level.
Like it must be the gene, or it must be the virus versus, wait a second, maybe it was the development pathway. Maybe it was something else. Well, I love this. Yeah.
Maybe a model in which this thing actually stores a memory of several possible outcomes, remembers what happened before, it can have some sort of valence as to what it prefers. Maybe that kind of model will actually help you manage the thing. And I dare say, I think we've developed over 20 years some applications of these ideas that actually show that we can move the ball forward in terms of science and therapeutics by not leaving all that stuff on the table.
I'm curious, any of you, what are you reading, that makes your brain hurt the same way you both made my brain hurt this week? In other words, like, what are you reading to kind of to push your own selves out of a comfort zone, or and it doesn't have to be science. I'm just kind of curious. Or how do you push yourself?
Speaking of pushing, I'm going to push a book I've been reading called Rise of the Replicators. And this is by Tim Taylor. Jean-Tine was mentioning philosophers like to go back in time, and Jana was saying the same thing. Tim's book really goes into, again, this idea that thinking about machines that self-reproduce, that evolve, maybe they're not that different from what's going on in nature. It actually has a very long history in Western thought and Eastern thought also, but in other forms. And I think, again, there's this, in the technological sphere, there's this flush of excitement about deep learning and neural networks, and this is all new. We've never been here before. We're making these extremely powerful machines. They're evolving. They're getting smarter. This is terra incognita. We've never been here before. I think history has a lot to teach us about. There are humans that have thought about this before. It might have been a little bit more hypothetical in their day, but there's a lot we can learn as we start to push forward into these, for some of us, non-intuitive ways of thinking. Jantine,
how about you?
Oh, I cannot, it's hard to mention one particular thinker or book. I really, so I think in my profession also, we really, go back to, say, the original literature when confronted with problems in philosophy or ethics that are currently a focus of also societal discussion. So one of the very interesting things is, and of course, people tell me, and I'm sure they also tell Josh and Mike, like the Frankenstein word, and that made for me clear, so I thought, what do I need to do? I need to read the original text, and then I got I understood what the original text is about and what it's saying, and it's absolutely not about. It doesn't even give any reason to use it in the sense people are nowadays often using it to with this moral intuition immediately condemn and label like a scientific field.
It is funny. I just started reading. I'm about 2 chapters or 3 chapters into Mary Shelley's Frankenstein, and I've never read it. And it's completely not what I thought it was going to be, And she was like 17 when she wrote it, and it's very interesting. What about, there are philosophers that are alive today that are probably going to be the original texts in 100 years, or a scientist like Mike, Josh, people that you respect or that you look up to, that you go, oh my gosh, that is just mind-blowing, or wow, I think there's something going on here.
There are many, and kind of too many to mention now. But I will suggest a strategy or something that I do sometimes to kind of help out the intuition. What you can do is take a paper from the field of neuroscience. Something that deals with higher level stuff. With memory or valence or preferences or any of this stuff. And you put it into Microsoft Word and you do a find and replace. And you replace the word neuron with the word cell. That's all. And then you just read it. And then you just read it. And so what you realize is that, okay, so you realize a couple of interesting things. So we've been, for example, we had a conference on basal cognition in Vienna a couple of years ago. And it was, somebody gave a really nice talk about the evolution of the nervous system and neurons, and so they wrote down some properties of neurons on the board, and then we had a 2-hour argument about what's a neuron, because actually every cell in the body does this, and so if all the things neurons do, all cells do it. What you can do is you can replace where it says milliseconds, you just say minutes or hours, okay, and after that. All the same stuff.
And then you probably get plants as well in there.
Sure, of course you do. Yeah. Absolutely you do. And so all this stuff works. And so what you can do then is you build this nice isomorphism, and you look and you say, wow, the field of computational neuroscience has tons of useful concepts for us, and work like people like Carl Friston are doing, and all this kind of thing that apply so much wider than the nervous system. It really doesn't have all that much to do with specifically the nervous system. It's much deeper than that. And so you can read things that way when you ask yourself, well, what was a neuron before neurons showed up? Well, of course it was, and in fact, they used to be bacteria. People have done really nice neuroscience in bacteria and bacterial biofilms and electrophysiology, bacterial biofilms. This stuff, evolution found this very early on. And so that's one thing that I like to do, is to see how much I can steal from these things and apply them outside of their normal context.
I like that. I was trying to think of a book that I would recommend, and I'm a big fan of the SFI and Santa Fe Institute, and have fun reading like Jeffrey West's book on scale and things like that. And one that I read last year that I really appreciated was Life Finds a Way by Andreas Wagner. And what I thought was interesting is that it actually has a lot to do with creativity in evolution. And again, when I first saw the cover and I started reading about it, I was like, creativity in evolution. Wait, there's creativity in it? There was a disconnect, but it actually has some amazing design patterns. I'm a designer, so a product designer. It has amazing design patterns to consider when you're trying to do kind of large leaps across metaphor or analogy space. You know, when you're not trying to do little baby leaps, but you're trying to really make leaps. And it relates to how evolution works. It relates to all this stuff. So I found it to be just a very delightful read. You know, I feel like I'm naively stumbling into these things. My partners in crime were trained by Herb Simon and J.J. Gibson, and people in the sort of economics behavioral space. And you know, in their world, we would learn about Simon's scissors, that the mind is not, you know, just the brain running the rules. It's the environment it's pushing against, and the beautiful emergence comes out where these two push against each other, and you get sort of stigmergic emergence, and you get all sorts of interesting things. But I also feel like, I mean, that's a original text. If you go back and read Herb Simon, I'm so curious about sort of who the new thinkers are that are pushing it even further, and how I might use that to learn about how to design a better physical place or a better community or a better thing. Because the things in physical places and all this stuff are the context. They, you know, context is decisive. We push against our world, and new things pop out at the emergence. And so, just fascinating stuff. Peter, what are you reading to get your brain to explode? Or,
you know,
who are
I've
you talking
gone talk about original text. I've gone back to a lot of times when. Right, when we've been looking at fundamental change and how we work through that. So as you know, I've been working on a project kind of re-examining world fairs and technology. So I love going back to in the 1930s when we thought, would there be an economic future? Would we go socialist? And suddenly there was all of this work about what sets of technologies would get us through, and then what bad decisions were made. You know, at that time we came up with FHA, but we encoded redlining and a bunch of other things. So we had, at a time of great change, we encoded a bunch of things that we're cleaning up from. And I get really interested in looking at stuff from then and thinking through how do we make decisions now at this very plastic moment, especially coming out of this pandemic, when we realize it's a moment that we can make important decisions about the kind of economic systems we have or the nature of how we design cities. So just in that 60, 70 year time frame, to me, it's a very useful thing to go back to.
Nice. I remember you showing me a giant poster that we printed out that covered like 40 feet. And it was a poster from, you know, Andy Warhol, and it was sort of the West Coast, East Coast dynamic of psychedelics.
That was from the 1960s.
I don't know what it was.
It was a diagram of expanded cinema. You know, so part of, I think, you know, picking up on what Jean-Dean said is, I think, or even some of the, you know, within category stuff, we keep thinking we're inventing something from scratch. So just as Mike points out, what we said about cells or what we said about bacteria actually applies to neuron, but at a different speed. This was in 1960 expanded cinema. It's what today we would call the world of immersive media or virtual reality, but they traced back all of these movements that were place-based and immersive and using emerging technology. And then they pushed it right back to Greek theater, right? So they looked at all of these things that we created to
chorus, yeah.
But in the 60s, there were just, you know, a whole range of these things, from the kind of immersive media that the Eames were doing to experimental happenings. And it was 40 feet of stuff. And to people, so people today who are working in virtual reality and immersive stuff and kind of all of this augmented virtual world, which, by the way, in the last year we've been completely pushed into because of the pandemic. It's amazing to show this generation, you know, just 50 years ago what was going on. And I think in general, this is true in the world of tech. Like here in Silicon Valley, the current generation of computer scientists aren't that up on what went on, you know, 2 or 3 generations before that. And so it was kind of amazing in this piece to go share that with, it was part of a talk I gave at Gray Area where we were completely excited about today's immersive media. And it was like, boy, have we been doing this for 1,000 years.
Yeah.
Very cool.
Fun stuff. Well, thank you so much for joining us. I know we've kept you, of course, long past time, and you jumped into this at the drop of a hat, and we really appreciate that. But you've given us so much to look at and think about and think in our head about. Any last words from anybody?
I wanted to just riff a little bit on what Peter was saying about, cinema. One of the things if you look at Hollywood, what are the scary movies about? They're usually about little creepy crawlies or robots. There's something about, biology, evolution, small things, and these machines that are not quite machines that fall in this uncanny valley. And they frighten us on an instinctual level, but there's something uncomfortable because they throw us back on our preconceptions. So that in terms of Hollywood got one thing right about robots, which is they don't care about us and they do threaten us, but they threaten our preconceptions. They force us to define, what do you mean by decision making? What do you mean by your inner life? And that's one of the things I think that's interesting about robotics and the work that Mike does and the things that Jean-Tine thinks about. And our technology is accelerating, our world is changing. We're really going to have to confront some of these deep preconceptions we have about how things are and how they should be.
What would you like us? What are the key things that we need to free ourselves from that will help us make better decisions and not mess things up?
Wow, that's a big question.
Seems like a whole nother hour.
I'm going to defer to my esteemed colleagues there.
I mean, big topic. The one thing I can say is this, oftentimes, and when I tell the story about cancer, and it's a kind of departure from the network and the body plan and all this, and people very naturally gravitate to this idea of, you reconnect them to the collective and then everything is good. So I want to be super clear that I'm not pushing any kind of blind collectivism. I think that is a terrible idea. And I think, and we know lots of history to tell us it's a terrible idea. I think what we need to develop are two kinds of things. The first is a way to identify better policies that simultaneously allow us to leverage what's good about being part of a larger scale individual, but at the same time maintain what's good about what we need. Because as you know, you lose skin cells all the time, and you spend 0% of your time worried about the skin cells that got destroyed when you did whatever you did during the day, right? So no one wants to be that disposable cog in this machine. And so somewhere between total this kind of total absorbance into a group goal versus your local individual goals, somewhere between there is a rational policy that optimizes both, ideally. And so we need new ways to find these policies, because we're not very good at it. And the other thing that we need, and I think that's part of why the work that Josh does is so important, and the Xenobot stuff is important, is we really need to understand where goals come from. Because for standard model systems, you can tell these stories that are evolutionary based, and it really hides the severity of the problem, because people feel like they understand where the goals of the, let's say, a zebrafish or whatever, and its different parts, where they come from. Well, they're shaped by evolution, and that's true. But that history is baggage, and all those frozen accidents of evolution are baggage, which hide this fundamental question, which is, placed in a novel environment, like when we create these Xenobots from scratch, you can see this is a new organism coming to be in front of your eyes in the space of 48 hours.
This goes back to your teleological kind of looking at it as purpose, not looking at it as how it developed that purpose. Well, we got to this point.
Yeah, we have to learn to predict. Never mind even all the sort of conceptual arguments about what kind of purpose it is and all that, but just to predict, what is it going to try to maximize or minimize or optimize? Yeah. What is this thing going to want? And so we are not very good at taking, and Josh can tell you, at taking a collective of subunits where you understand what the subunits are doing, linking them together. Can you tell what the whole thing is going to try to do, or what is it going to want? What is it going to pursue? What state of affairs is it going to spend energy to bring about? We're not very good at guessing that, and we're terrible at managing it. And we're going to be surrounded by this stuff. We already are, but we're even more so. We really, to optimize human happiness and welfare, for the whole biosphere, we really need to get better at understanding where in these kinds of systems, where their set points, their homeostatic set points come from.
Well, this reminds me of Kevin Kelly, his book Out of Control and What Technology Wants. And, he's been thinking a lot about this for a long time. And that notion of the objective function, that we hear so much about in machine learning. What is the objective function, and how do we even understand that? I was really I loved reading This View of Life by David Sloan Wilson, who he wrote a paper with Edward O. Wilson in the 90s. He's an evolutionary biologist, and Edward O. Wilson is as well. And what I loved about it was, I have the quote here. He said, they both in the paper said, selfishness beats altruism within groups. Altruistic groups beat selfish groups. Everything else is commentary. And I thought that was really curious. I mean, it goes to the why humans are cooperators. But it, and I, of course, I would love to challenge that too. But it is an interesting thing to say, how do we make sure that we're not selecting at the wrong level of selection? And how do we look at, and he talks about Tinbergen's 4 questions in evolution, which I had never heard of. Again, as a designer, I went through a different education. But it was quite interesting because a lot of it had to do with development and some of these other questions aside from purpose. And you don't realize, like, even in this notion that cold-bloodedness, why did it mostly evolve on land? Well, geez, water sucks away the heat of everything pretty quickly. So, it was just harder to manage your body temperature. So that's that probably shaped things, and so there's all this stuff that I think we're very naive about, and we look for the simple answer. And yet there are probably hidden theories and rules that we could learn from in life for all this work. Okay, I think we should wrap at some point, don't you think? This is how dinner goes, though, isn't it? It just keeps going. It's a Friday night. Jantine, any last words?
Yeah, well, I think, from the philosophical point of view, this whole conversation is an excellent demonstration for, of how I work and why I work this way, because we see how incredibly, fruitful and productive these encounters are, and taking taking also the freedom to go into these conceptual questions, and that is what I mean with like bio-inspired humanities, because it's not only philosophy, it's probably also other humanities, and yeah, for me the only way to do it, and how I have gotten to the point where I am, and also not being afraid of this encounter, that is this collaborative ethics, or the collaboration and aspect, and it's an incredible privilege, like in a place like the Wyss Institute for the bio-inspired engineering, which is already breaking boundaries of what we usually things that we usually separate conceptually. So yeah, I enjoyed it very much, the conversation. Thank you
so much for joining.
Thank you. The span of, if you think of the dynamic range of this conversation, we've talked about these fundamental philosophical concepts, and then Mike brings it right back to how does this help us approach things to the most practical experiments to go solve these pressing medical problems. It's really lovely to kind of see that connection and how all these things work together. This has been, first of all, Mick, thanks for inviting so much great talent, and also
I just sent an email. They're the ones who said yes, so I appreciate it.
and Josh and Mike, thanks for sharing. When did your article come out? That came out pretty recently, didn't it?
About a week ago, right? Yeah. Something like that. Yeah.
Yeah.
So we're thrilled to like with this news. I mean, I think Josh, you mentioned the fact that this is kind of a moment of terra incognita, because we're looking at things in such a fresh, reframing way. So we're kind of thrilled to have you on and to work through this as it comes out, and that kind of helps set an agenda for understanding how we're going to think about machines and life in the future.
Thanks so much for having us.
Thank you very much. Yeah, this was fun.
And
thanks, everybody.
Okay, now since Omid left, I'm going to see if I can thank everybody.
You're in charge. You got to
just like this. Watch this. Here
you
we
got
go.
to push the people away. There we go.
And thanks very much. And here's one more to go. And boom, there we go, Mick. We have once again merged the virtual with the real, because it's back to us here. That was great. And next week is going to be our first anniversary show. Because we first started this They actually 1 year will be this coming Wednesday.
It seems like everything is an anniversary. This week, last week, next week, they're all anniversary shows because we're looping back on the time when we all went into shutdown. I almost feel, weirdly, your phone now shows you like, this is a picture from a year ago or whatever. And I almost wonder, there's a part of me that wants to do a retrospective. And then there's a part of me that wants to go, there's got to be a reason why humans forget things. And why do these social networks keep on wanting to remember things? I know it's just to capture my eyeballs, but what would we do as a retrospective? What are you thinking about for next week?
Well, first of all, we're going to have Drew Youngs on the show.
Oh, okay.
You know who Drew is the guy who wrote our theme song.
He did the music.
Drew is our music director.
He wrote the retro 1950s. Now, I think you gave him some audio to listen to from the 50s or 60s.
We're going to interrogate what was our original intent. What did we imagine going into this quarantine moment? Which
I only said yes to because I thought it was going to be a few weeks, by the way.
Yeah. Well,
because I don't, yeah.
Yes, and this may be saying something about innovation because people thought there was a short period of time and it was a sprint, so they gave it a sprint effort over a year. But anyway, we're going to do that, and then we're going to probably look back at some of our top themes, and most importantly, we haven't figured it out yet because the future hasn't happened. It won't be.
It hasn't happened. We can't really plan for next week until next week.
Yeah.
What time is it?
It's, we used to say it was uncertain, but I think that today kind of connected that up. So we now know with some great certainty it's actually 5:50 Pacific Quarantine. By the way, a term which we at the rate that we're vaccinating people, we may have to lose that term pretty soon. We've talked about renaming the show from Quarantine to Endless Frontier as a nod to both Vannevar Bush and the fact that if we thought we had an amazing future ahead of us in 1945 when he wrote his report, President Roosevelt, if there's one thing we've learned today, things are accelerating and that frontier is becoming even greater.
There's a lot of work to do. Yeah.
Which is why we're here.
It's so big. Yeah.
So
well, thank you, Peter.
Everybody, and we will see you next week when once again it's quarantine.
Let's get